So in the last class, we tried to really look at something named streamlines, streak lines, and so on, so kind of definitions. Try to really look at very simple one. If some point particle is at one location, if it is subjected to certain velocity field or already velocity field is there, then how a particle really traverses in time from one location to other location we have derived. In the same time, we try to really look at what might be these imaginary streamlines throughout the field at a given instant of time. That means I just know the velocity field. So can I really visualize a qualitative picture instead of talking in terms of velocity? But can I really see something like moving from one location to other location? That's what we call streamlines, and that's also we try to look at it. Now we are trying to ask slightly more complex problem like a garden hose problem. For example, you have a tube garden hose and it's rainy day, so it doesn't make sense to really release water out. But let us consider it is very sunny day and you have a garden hose and you are watering plants. But you are just a kid and you want to play with the garden hose. You are making it to oscillate. If that is oscillating, can I really describe the flow field information? Can I really describe a particle, fluid particle, which is discharged from that garden hose at a given location? This kind of things, can I really draw it, visualize it, and so on? That is the step what we are trying to look at. Can you confirm me? You can see something like video? Yes.
Yes, sir.
Great. Let us consider an example for path line and straight line. An oscillating jet in an unsteady flow. You hold a garden hose and liquid stream is coming out of it. Now, either hold it steadily or try to oscillate this up and down, this garden hose. When it is steady, you are just holding it. Let us assume that water is discharging out. Like a spring. You look at any fluid particle which is left at that location. Once it leaves the hose, it tries to go in a rectilinear way in this direction. Perhaps this fluid particle on other line try to go in that direction once it leaves the hose. Whether you are shaking it up and so on, once it leaves that hose in a rectilinear way, the fluid particle try to travel further. The fluid particle which is released there, you are trying to shake it up and down. Once it leaves, whatever the tangential velocity it has acquired, in that direction, fluid particle traces. That's what we call path line. So any fluid particle with one particular direction, once it leaves, if I am not considering any air drag and other thing, that particle goes to this location next instant of time. Next instant of time, it travels to that location, from there to there, and so on. So this is a path line. Now think of, for the same liquid jet, you are moving it up and down, swinging it, the garden hose, and also you are releasing some dye, color dye, blue color dye, red color dye, and so on. So one after other, blue color dye is coming out of the system. Now, when you are moving it up and down, the blue color dye starts showing a sinusoidal kind of oscillations with the flow as it is going out, because you have a up and down motion of fluid particles. So one after other, fluid particles really comes. The first fluid particle comes out with one tangential velocity, goes in that direction. Next instant of time, another fluid particle really comes, which is coated by blue color from the same location of this jet, but having a face, it will be at another location. Because this garden hose is going up and down continuously, the fluid particles, whatever released, sometimes released at this mean line. So if I am drawing, with the time, one fluid particle might be released at that location. Next instant of time, garden hose moved to next location. So next instant of time, fluid particle might be released at that location. That means this fluid particle already travels to that location. A. The next instant of fluid particle released at that location. If you look at further, the next instant of time, the fluid particle C might be released at that location. By that time, A might have traveled there, B might have traveled to this location, C might be there. So if you are on average looking at that, the time when it is going down this hose, the release of these fluid particles also goes down. So effectively, you start seeing a sinusoidal kind of pattern. And this is a streak line in that situation. Because all these fluid particles, the blue color dyes, are released from the same nozzle at that location. So you freeze in time and try to observe. Now, is it possible for you to derive the equation for that sinus pattern based on the garden hose up and down motions? So can anyone answer that? Hello? Hello guys, am I audible, not audible?
Audible.
So if something like if I'm asking a garden hose is going up and down, I would like to really sense path line and streak line of these particles. How to derive that, deduce that? Can you think about it? What exactly I'm supposed to do? Any lead?
Sir, like in y-axis, the motion is can we think as of SHM, and in x-axis linear motion. So we will get some uh, relation from there.
How? That's what I'm asking. Fine, there is a SHM motion for this jet, perfectly fine, the garden hose. But I'm just curious to see the path traversed by that particle, what I'm supposed to do. That's all I want to know.
So y is a function of time and x is a function of time. Then we will solve that.
So first you have to really originate some location. Once you originate, you should really know what is the jet speed with which these particles are coming out. Once they release, we should make sure that dxp by dt is equal to that particular velocity, and dyp by dt is the transverse velocity created by this jet up and down oscillation. That means based on the up and down frequency, I should be in a position to really connect what might be the function, velocity function at that location where a particle is going out. If I have these two information, then that I can just integrate it. I will be in a position to really get something like sinus kind of oscillations. We will derive it in the next class when we have 2 hours kind of class. It takes some time. But let us look at the reality, how complicated these oscillatory flows are. Though the example, it looks like a garden hose problem, it has very big applications in terms of rocket engine exhaust. How these oscillatory exhausts really comes out of that nozzle, how one can really achieve thrust with the different kind of directions and so on, so kind of stuff. That kind of one application, first of all, we will try to look at it to sense how difficult or complex the fluid mechanics part of it. But still, your kinematics really helps us to reveal the structure where exactly fluid motion really happens.
Let us consider
once
an
again.
example for
Yeah. These are called Lagrangian coherent structures. Basically, there is something like a fluidic chamber. People try to understand that something named control devices. We will first of all look at that animation, then I will explain you what's going on. So you have a chamber. This is, you can think of more like an exhaust kind of chamber. Something like exhaust gases are really coming into picture. Some part is diverted at this part. Some part is diverted at this part. When the diversion is happening, flow which really comes in one of these partition chambers really makes this entire exhaust gases to some kind of control mechanism. It works in that sense, whatever the liquid really comes out of the chamber just goes, push it here, it creates some kind of sinus oscillation. Those sinus oscillations really comes out, goes up and down, and that is the way you create this micro thrust devices for rocket engines. Maybe there might be a spacecraft which is in the space. You would like to really have sudden diversion of the spacecraft thing. The way how you really achieve it in space is you cannot really create those thrust forces so spontaneously. For that, you will use this kind of passive and active control kind of chambers. Once you understand, hello,
Yes,
guys,
Yes, sir.
you can still see the video, right?
yes, sir.
Yes.
Wonderful. So basically what you do is passively you try to extract some amount of liquid from one of these partitions, try to refeed it back. You know the mechanism, like how it really works, how the small scale vortices, what we call, really goes, becomes big, very large, try to push that liquid all the way down and try to create this kind of control and try to reduce these the dynamical systems configurations and so on, so kind of thing, so that you will achieve something. Once you achieve that, immediately you switch off that fluid which is entering that nozzle. That is the way you suddenly quickly get something named thrust. Because your mechanical things, you cannot really change it. For example, like you can really think of, maybe I can really have some mechanical device, maybe I will have a servo motor which I will really divert it so that my nozzle really goes in the downward direction, so I can really get a thrust. But if you are going to achieve it in that way in space, what will happen is, because there are no frictional forces which will resist, immediately entire spacecraft start rotating. So instead of that, what people try to do is they will have this kind of passive chambers. From that passive chambers, by just pumping these exhaust gases or these combustion gases into that, maybe stopping it, they can really make sure to grow that fluid around that loop. That can really achieve diversion of the liquid jets. That way, they control the chambers to achieve it. Now, if I play it once again, you have to tell me whether what you are looking at is something like streamlines, streak lines, or more than that. Can you see the picture animation? So you will not have any moving parts. That is the advantage of this kind of fluidic oscillators. It's up to you if you are going to switch off these gases, whatever coming at this entrance of the chamber. You can always control the mechanism. And this kind of breaking up of parts, what you call turbulent motions. So complicated even to describe it. And I'm sorry, can you see that? It is sponsored by Boeing company. It looks like very simple problem. What is so great? The fundamental research actually begins in that way, which will be inspired by industrial applications. So though the garden hose looks like very simple and nice kind of problem, but it has very important implications. So you will avoid completely moving parts. That is the advantage of this design. This is what you call PIV, particle image velocity metric. So you sprinkle a lot of smoke or particles, tiny kind of things, you visualize the thing. Now the colored one is dye. So it's supposed to be your streak lines. Now what they are trying to look at is different zones they are trying to look at. Very slow speeds, how it really looks like, and so on. Now the question, if I would like to really visualize or reconstruct it mass, how complicated the story is. And how far these jets really goes all the way down the stream. This is what you call downstream. This is what you call upstream. These are what you call coherent vortices. We will learn about them, we will derive them, how to mathematically quantify, how they grow with the time. What makes them to grow? Why they should grow? Why can't they really disintegrate into pieces? How do they get that energy? At hand waving C, there is liquid jet, energy is gained and so on. But what makes it? How these liquids really get deformed? Why such kind of oscillations? So many questions always be there. You see, the motions are so complicated. It's not like your typical Newton's equation of motion where balls are coming and impacting each other. It is much rich in science. And definitely what you are trying to look at are not streamlines. So shall we move to go further in mathematical quantification of this field named kinematics? First of all, let us begin something named steady flow, unsteady flow, one-dimensional flow, and so on, so kind of stuff. The basic definition of a steady flow is flow doesn't depend on time. Or you do long-term averaging, you see the same picture. In that case also you will call steady flow, but a kind of crux word you use as stationary flow. For example, let us think of a pendulum doing to and fro oscillations. At any given instant of time, if you are looking, the bob is always be oscillating. You can always say it as unsteady. But on long-term average, if you are looking at that, the bob always be at its mean position on long-term average. If that long-term kind of description we call stationary flow or statistically stationary flow or statistically steady flow. If I am saying steady flow, you pick any instant, the next instant, the next instant, you see the same information. That means there might be something like a river flowing. You take picture. The same information you are going to see next instant of time, next instant of time, next instant of time also. Then you will call a steady flow. Unsteady flow is bit more complicated. It always depends on time. For example, sometime back we have seen oscillator, fluidic oscillator. Flow at any given instant of time, you are going to look at the picture. It differs from the next instant. That means if I am going to take snapshots one after other within a time period, where a fluid jet goes up and down. Within that time period only, if I am going to take snapshots one after other, every picture differs from each other. That kind of flow, what we call unsteady flow. There is one more keyword named one-dimensional flow. A flow, if we are taking pictures, you all the time sees it moves from one location to another location along one particular axis. That kind of flow, what we will call one-dimensional flow. For example, in the same microfluid, not micro, I'm sorry, in the same jet fluidic oscillator, flow at the entrance all the times comes from left side towards right side. Very entrance is one-dimensional flow. Within that chamber where it starts showing oscillations, it is two-dimensional because sometimes it goes up and down and sometimes it goes forward and so on, so kind of thing. It spreads all the directions. That kind of fluid, what we call two-dimensional flow. The flow which really comes out of the jet shows very up and down oscillations every instant of time. It differs. That is unsteady flow. So in a given engineering configuration, you can have mixture, depends on which region you are trying to look at. There is nothing like perfectly steady, perfectly unsteady, perfectly one-dimensional, perfectly two-dimensional, and so on. In any engineering device, you may have all these combination. Maybe if you are switching off your ceiling fan, flow might be coming towards the blades and trying to divert. Maybe very near to that fan blades while it is converging, it might be one-dimensional flow. It might be steady at that location. But while it is coming out of fan blades, it goes all the directions. Maybe it might be two-dimensional, three-dimensional. Maybe near these edges of these rooms, sometimes crosswinds are coming. So it might be even unsteady. That kind of combinations happens. So just to give you flavor for the, I'm showing you something like a water coming to your houses through pipelines. Maybe there might be overhead tanks. From there, there will be pipelines which are bringing all that water all the way to your houses. You are going to open the tap. Maybe as water really comes out of it, it starts showing this kind of sinus oscillations. These sinus kind of oscillations, what we call unsteady. They might be two, sometimes they might be three-dimensional in nature. And they will be steady maybe at the entrance. And the lines, what I am trying to draw, maybe if I am going to take a picture, based on the tangent velocity vectors, if I am going to really describe some picture, I will call them as streamlines at a given instant of time. Maybe if I am going to really track individual things, I will call path lines. Maybe at a given instant, at a given station, I discharge a lot of colored dyes. That colored dye, how it really goes at any given instant of time, maybe I'm calling strict lines. So that kind of description, what we will call kinematics. And in this kinematics, all the time, we talk about something named field variables. That is velocity vector, a vectorial field in x direction, in y direction, in z direction with the time, what happens. Similarly, the vertical velocity component v, how it varies in x direction, y direction, z direction and time. This kind of description, if we are going to look at, we will call kinematics. Their derivatives, their cross products and so on, so kind of things. Just to give you further more information, if I am schematically showing, maybe you take a pipe, the argon pipe, you try to blow air into that. There might be compression, rarefaction fronts happening. You continuously blow air into that system. Maybe it might be even a fluid. Maybe if fluid really saturates at one location by this way, again at some other location, again at some other location. Something like isolated patches you are seeing. It doesn't depends on y direction, but it is only in terms of x direction. Such kind of flow configurations, what we will call usually one-dimensional flows. That means if I'm, because velocity is always be vectorial quantity, I always be having something like that kind of direction. Maybe I'm going to decompose it into x directional and y direction. This is at each and every point in the flow field. And that kind of configuration, what we are trying to look at is here. Very simple thing. Something like fluid comes here in one direction and it leaves in that one direction. So u is only function of x coordinate. This is the x coordinate. U doesn't vary in the y direction. In case if such kind of information available, we will call 1D flow. It may not be only u, even it can be v only depends on y. V depends only on x. V depends only on z, only on one spatial coordinate. If it depends, we will call 1D flow. Can you give me another example of one-dimensional flow in reality, what you might see? Can you guess? That means you are going to really look at velocity field. It should not depend on other coordinate, but it can depend only on y coordinate. That means it might be high here, this might be low there. Again high, it can be low, but it should not depend on other coordinates. Can you think of it? Hello? Guys? Hello?
Yes.
Go ahead. Can you guess? So if you are thinking of something like your automobile exhaust gases coming out of silencer, well before silencer, if I am really thinking of the system, this pipe, whatever that just before the silencer, the pipe dimensions are so narrow or so small compared to the muffler or the silencer or compared to the atmosphere, the entire flow comes from one location to other location, acts like one-dimensional flow compared to the flow which enters the muffler or the silencer. Because at the silencer there is so much porous kind of media, whatever this flow really comes is star splitting, goes in upward direction, downward direction. While it comes out of the silencer, it really discharges into atmosphere, it start mixing and so on, so kind of stuff. So in this entire big process, maybe the small part of that exhaust pipe, which is just before the muffler, can be thought as a one-dimensional system. So that's what I'm trying to say. Nothing is one-dimensional, two-dimensional, three-dimensional kind of thing. It depends on what kind of configuration compared to what we are trying to compare. We usually say that this is one-dimensional, this is two-dimensional, and so on. Maybe you are looking at a river, very big river, maybe Ganga. If you are looking at very near Varanasi on the Ghat, you look like something like flow comes from one location, goes in other location, and so on. It must be two-dimensional, it must be three-dimensional, and so on. But if I am looking at space, there might be very narrow stream of liquid really comes. Maybe I'm going to really look at one particular patch, it is straight line. So in that configuration, if I am looking from space in that narrow strip, I don't really care about lateral oscillations because laterally it may not be more than 2 kilometers, 3 kilometers compared to a length of 10 kilometers or 20 kilometers of stretch. The stretch is 20 kilometers very straight compared to lateral 1 or 2 kilometers. In that case, what I will really worry about is Ganga comes more in a one-dimensional way in the stretch. That is the way people usually talk about it. It depends on what exactly you are trying to look at. Maybe you have a pen in your hand. liquid continuously discharging as you are writing. On the paper, the liquid might be two-dimensional, but the liquid, whatever discharging in the refill, can be considered as one-dimensional. Maybe you might be taking something like a injection. The liquid which comes from that needle, within that needle, can be considered as one-dimensional, maybe, compared to the liquid which really comes into your veins and start mixing. That is the way people try to really make approximations. Okay. Now, if your objects show variation in velocity in some other direction like y, but that velocity doesn't vary in the x direction. Can you see here the second example? Hello.
Yes, sir.
Yes.
There is something like a tube, it can be needle and so on. In case if we are somehow sensing the velocity field information, the way how you visualize any velocity field is, or vectorial field is, by arrows. Each and every location you draw velocity vectors. How they really look like. Maybe if I am going to really look at this section, it can be complete round pipe, it can be something like a slot. Here the velocity is 0, let us assume. Here the velocity is 0, so just a point. But here there is a velocity. I'm showing at that location, if I'm going to keep a probe, how strong that velocity, maybe 1 millimeter per second. As I am going in the vertical direction, it might have decreased to 0.5 millimeter per second, 0.25 millimeter per second, and so on, so kind of stuff. All these things I'm going to connect it by a line, because there is no velocity in the upward direction. That's the reason my velocity vectors are not oriented in the vertical direction, but only in the horizontal direction. In that case, if I am going to really look at this horizontal velocity component, horizontal is this, which are u components, depends only on the y, but not on the x coordinates. Whether you measure at this location, 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 u is only function of y, but not on x. That kind of flows are also one dimensional flows. Is this example clear? Hello.
Yes, sir.
Yes.
Wonderful. Now let us look at some other example. Maybe you have something like a converging chamber. Is more like your mosquito needle or very sharp needle, where the cross-sectional area means maybe it might be something like that. So liquid comes, liquid goes. It's more like your garden hose. That what I am trying to do is make a vertical cut section, so that this is the one. This is the cut section of the chamber. Liquid can't really get out of this cut section. Liquid enters with some particular kind of shape, where u is function of y at this given section A. Next, at another section you are looking, again it looks some function of y, but compared to this velocity profile increased. Here if it is something like 1 millimeter per second maximum, here it might be 5 millimeter per second at maximum. Here it might be 10 millimeter per second. And also it varies in the vertical direction. If such kind of flows are there, we will call two-dimensional flows. I'm sorry. And these two-dimensional flows, where any of the velocity component is function of two coordinates. It's not necessary that you may have two velocity components. You might have only one velocity, that is horizontal velocity, but it depends on both x coordinate and y coordinate. That kind of coordinates thing we will call 2D flows. The same 2D flow may even look in this way. Let us consider u component is completely function of x, because vertically it is same. So u is not a function of y. The same velocity you are going to see. But at different location, that u component has increased. That means u is only function of x. When such kind of things are happening, because of mass continuity equation, which we will learn it at later point in time, naturally v components are also get generated. Without that, you cannot maintain the system. You will start seeing both u as a function of x and v components as a function of y. It's supposed to get generated. Why it will do that, we will see later. In that kind of cases also, we will call that one as 2D flows. That kind of configurations also we will see 2D. Oh, I'm sorry. Let me write it. These are the terminology what we have to really know to talk about 2D flows. Wonderful. Let us consider another example. Maybe you might be having bridges, maybe there might be aeroacoustics, or perhaps something like you want to extract energy from wind. So flow is passing over this particular object. What you are again seeing is something like a cut section. It can be aerofoil kind of shape, the blade. It can be even something like cylinder, rectangle, and so on. So thing. Flow comes at one location, goes, and it detaches, starts showing something named Karman vortices. We will learn about that name. Such kind of configuration, usually 2D flow, because u is a function of x comma y coordinates. V, vertical velocity component, is also function of x comma y coordinates. And also sometimes these vortices which detach from the flow can be function of time also. Such kind of configurations are also we will call 2D flows. Shall we look at one short example to really see mathematically how to quantify these 2D flows, 1D flows? So let us look at this example. Very simple thing. Write unidirectional velocity field u is equal to some constant capital V multiplied by E bar y in spherical coordinates, and the uniform flow u some constant capital U multiplied by E of r in Cartesian coordinates. If we talk in terms of math, it will be in that way. Here, what we are trying to see is to appreciate how these one-dimensional flows really look like. That's what we call technical word named unidirectional velocity fields. That means your u components, the velocity vectors, if I am using this underline, that means it's a velocity vector. It acts only in the y directional information in that particular unit vector. So E underscore represents unit vector in the direction of y. And it has some constant V naught or V, capital V, which is different from your small v. It can be even capital A multiplied by E bar y. This capital A may be function of y, it can be even function of x, it can be even constant. But what we will have is it depends only on one particular coordinates. Can you visualize how that flow field really looks like? If you want to really draw that particular velocity field, if someone really talks in terms of math, unidirectional u is equal to v e y, can you visualize it how it really looks like in x Cartesian coordinates and also in spherical coordinates, in cylindrical coordinates? Can you visualize that? That is the example what we are trying to look at. So that means maybe if I am really showing you visual, the pictorial thing, which is very easy to see, there is something like xy coordinates. Maybe you are going to take a picture from satellite. X-axis is in one direction, y direction is this, your satellites towards that is z direction. You are taking a picture. Maybe river gush happens from one station, maybe from some Gangotri, it goes towards some Haridwar. In the stretch, at a small stretch you are trying to look at, which looks like more like a straight line. Maybe this is Haridwar. Throughout, it is something like 3 meter per second, 3 meter per second, 3 meter per second, 3 meter per second throughout that width. Maybe from Rishikesh all the way to Haridwar it is going. Everywhere you look at it, it is 3 meter per second. It doesn't depends on which y location you are looking at. That might change to 5 meter per second as it is reaching Haridwar. This is perfectly fine. But throughout the system, you are supposed to see it should depend only on one particular coordinate. If that happens, we will call one-dimensional flow. It can be even same 3 meter per second here, same 3 meter per second. That's also possible. That's also one-dimensional. Maybe it can be 3 meter per second here, but here 1 meter per second. This cannot be possible because of this mathematical constraint. You understand, your velocity is supposed to be only in the y direction. It's supposed to depend only in that y. That means I cannot have 3 and 1 pictorially if I am speaking. That is what we call unidirectional flow represented by this mathematical function. It should depend only in the y direction. It can be constant. It can be vary in the y direction. Hope that math is clear. Representation. Fine. If I would like to really convert that system into spherical system, because I want to really look at Earth as a sphere. I don't want to really look at Cartesian, even from that Rishikesh to Haridwar. I would like to really convert that component. What we will really do is, okay, fine. U in spherical coordinates always be represented by UR, U theta, U phi. In Cartesian coordinates, it will be represented in terms of Ex, Ey, Ez, U, V, W kind of thing. Now, if I would like to have something like radial coordinates, what I have to do, pick any of your U velocity vector, dot with particular radial velocity vector, you will get UR component. That means your U in Cartesian is your U, V, W. That means U multiplied by EX plus V multiplied by EY plus W multiplied by EZ. This is the vector independent of whether spherical coordinates, cylindrical coordinates, or any other coordinates. That if we are going to have inner product, we will be going to get that particular component. Is this step clear what we are trying to do? Hello?
Yes, it is clear.
Wonderful. If that is clear, U component is VEY dot with ER. So EY, ER coordinates, how they are going to dot. For that purpose, just give me 2 minutes, we will close the session. If I am visualizing X coordinate, Y coordinate, and Z coordinate, something like a point P here, and this is the radial coordinates. X is equal to the projection R. So now I have to really fix in terms of coordinates. Something like theta coordinate is from the Z direction. P coordinate is from X axis. If I am going to really look at it, the projection of R into sine theta multiplied by cos phi gives me my X coordinate. So R sine theta project it. So it goes down, then project further into cos phi gives me X coordinate. Y coordinate comes as R, project it onto XY plane. So that will be R sine theta multiplied by projection of sine phi. So that is sine phi. Similarly, Z, if I would like to have R cos theta. This is the rule what I have to really see. Why I am saying that is, now we would like to really have inner product of ER coordinate with EX. That means project ER onto EX. So that gives me any radial component. If I am going to project it onto X, is basically my any vector U going to have a projection in terms of radial. This is the thing what we are going to look at. So that means my R sine theta sine phi ER is the first coordinate, where EY ER product I'm going to write it as V sine theta sine phi, the way how I am going to project it. So my total velocity component in the spherical coordinate system becomes UR, ER, U theta, E theta, U phi, E phi is V sine theta sine phi, ER, the projection, X coordinate projected onto spherical, Y coordinate V cos theta sine phi multiplied by E theta, and V cos phi, E phi. So based on how you project R coordinate onto X coordinate or X coordinate onto R coordinate, theta coordinate, phi coordinate, one can really write this velocity vectors. So just rework it out. You will understand how to convert Cartesian system into spherical system or spherical system into Cartesian system. Anyway, we'll come back in tomorrow's class to see more details about that math. Try to really look at those information, write these kinematics and so on, so kind of stuff. See you in tomorrow's class. Bye.
Bye, sir. Thank you, sir.
Thank you, sir.
Excuse me, sir.